if you've got a formula, the first thing you'd look for is, are there metals? So I can make a flow chart here. It'd be helpful. So if there's a metal involved versus if there isn't, no metal present, then if there's a metal involved, it's either a metallic, solid, or ionic. There are some exceptions to these, but we didn't talk about them, so we'll just keep it simple and not worry about that for now. If there's no metal present, it should be either covalent or molecular. So then, if there's a metal involved, what you have to ask is, are there also, along with that metal, any nonmetals? So if there's no, so I guess I could say if there's only metal, then it's a metallic solid. So that would be, for example, like sodium or iron, something like that. If you have a combination of a metal and a nonmetal, then it's going to be ionic. Oops. So that would be like NaCl or FeCl3 or MgBr2. So that's the easiest part. Determining the difference between covalent and molecular is a bit trickier. So the way to answer that is going to be really, can you draw a Lewis structure that gives you a discrete molecule with a finite number of atoms that can all share the electrons and make their noble gas configuration with the formula you have. So you could say formula allows for a stable Lewis structure. So that would be something like a CO2 or a C6H5. Oh, there's thousands of examples. If you can draw a stable Lewis structure, then chances are you'll have a discrete molecule and that'll be a molecular solid. Where the atoms are sharing electrons in covalent bonds, but you have molecules because that molecule is not bonded to another molecule through a covalent bond. In a covalent solid, you can't really draw a discrete Lewis structure usually, because if you have an atom in a covalent solid that's sharing electrons, you might not even have a formula. It might just be like carbon or glass or diamond or something like that. Because in that case, you can't really, you can draw a formula, but what's the smallest repeating unit for a diamond? The smallest repeating unit for a diamond, draw this. So that's your smallest repeating unit for a diamond. Does that look like a stable, discrete molecule? No, none of the carbons have 4 bonds. They either have 2 bonds or 3 bonds. So this cannot be a molecular solid, because to be stable, it has to continue. I have to continue this solid in all these directions and continue this structure three-dimensionally into a network of covalent bonds. So that's when you get a covalent solid, when the atoms involved need to keep making bonds in all directions in order to complete their noble gas configuration, so you have a network that extends in all directions. Another example would be something that's cross-linked. We didn't really talk about this, but I mean, we briefly mentioned it. I don't think we used the term cross-linked, but that's if you have a polymer, which is a chain of atoms. Normally that's a molecular substance, because the chain is a discrete length. It has a certain number of atoms of carbon and hydrogen or whatever else is bonded to it, and those atoms share electrons to complete their noble gas configuration and make themselves stable. When I cross-link it, though, that means I've got a bunch of chains around here, and all my chains are maybe overlapping to some extent, but then the cross-linking process occurs when the chains get connected to one another. And so now it makes a molecular solid into a covalent solid. Because originally I had discrete chains that were an intact, self-sufficient molecule that had all the noble gas configurations completed. But then if I connect that through a covalent bond to the other molecules and I make a network between them all, now I have a covalent solid, because there's a network of connections from one atom to the next all the way through the material. So often for a network solid, there's no discrete formula.